Welcome back, guys. All right, guys, we're just proceeding through our curve sketching units, and the next topic is what we call the first derivative test. Okay, so here's what we mean by that. If we say a function has an absolute maximum, that means the function has an absolute max c if f at c is greater than or equal to f of x for all x. So if we look at a function like this, say we have a degree, like a quartic function, so there's like a degree 4 polynomial here. If you look at this point over here, like this graph goes down forever to the left and down forever to the right, this point here, this y value, is the highest y value that we have. Okay, so this is going to be called an absolute maximum value. Okay, so there's the absolute max. Okay, now this function over here does not have an absolute min because the graph keeps on going down forever both ways, so there is no absolute minimum. Now this point over here is sometimes what we call a local minimum over here. Like this point is smaller than all of the points around it, but it's not the smallest point overall. Same thing, this point is what we call a local, or sometimes we call it a relative maximum as well. So it's bigger than the points around it, okay, but it's not going to be the biggest point overall. This is the absolute max, this is a relative max, this is a relative min over here, okay? So here's kind of definitions of absolute max and absolute min. And there's something called the extreme value theorem over here as well. So what this says over here, sometimes a function is only defined over a particular domain. The function is defined over a to b, then f of a or f of b could be the absolute max or min. So let's look at the same function we had over here. I'm just going to try to sketch this one again. But let's suppose it was only defined from a to b. So let's say I had this guy over here. Okay, so here's like our x value of a and our x value of b over here too. Okay, now in this case, okay, this guy does have an absolute minimum. Okay, so since we're stopping the function here, this is the lowest point on the graph. Okay, so what is it saying over here for the extreme value theorem? If f of x is continuous on the closed interval from a to b, then f of x must attain a minimum and a maximum each at least once. That is, there exists a number c and d such that f of c is less than f of x, which is less than f of d, for all x an element of ab. Just a lot of weird notation over here, guys. This upside down a means for all. This weird e means an element of. Okay, so what it's saying is that our function f of x has a lowest value, f at c, and a maximum value of f at d. So in this case, this y value here would be f at d, and this y value here would be my f of c for a graph that looks like this. Okay, sorry guys, I copied this one down twice. Okay, so let's look at this guy over here. Consider the function f of x equals 1 over 24, x cubed over 3 minus 36x. What is the absolute max? Okay, well, there is no absolute max because, guys, anytime a graph gets cut off like this, we assume that the graph keeps on going forever like this. Okay, even if there's no arrows drawn on the graph, we assume it keeps on going. Okay, so there is no absolute max, and there is no absolute min. Okay, now again, we're talking about a relative, or something we call this a local max or a local min. Hopefully you agree that this point, which looks like 6, is the local maximum, and that negative 6 is a local minimum. Okay, so how do we figure this stuff out algebraically? Okay, here's our function. Now, what I'm going to do over here is I'm going to take the derivative of this guy. So f prime of x equals 1 over 24 of x squared minus 36 is 1 over 24 times x plus 6, x minus 6. Now, if you recall from our last section, intervals of increase and decrease, I'm going to put in a -6 here and a +6 here. I'm going to do my test. If I take a number less than -6, I get negative for positive. And then in between here and here, I get positive, negative, which is negative. And then I get positive, positive in my last interval. So I get a positive region over here. All right, so here's what the first derivative test is saying. We've done a first derivative and we've done a number line analysis. Okay. Now, first of all, -6 and +6, these are functions, these are points in our domain. Okay, so this function is defined at -6 and +6. This is a continuous function for all real numbers over here, so that means it's going to be defined for all x values here as well. Okay. If we see that, if we can see this clearly, guys, it's going to be less clear if you don't have the picture in front of you, but what this is saying, from -infinity to -6, the function is increasing. And then our derivative is 0 at -6. That means we have a horizontal tangent here. And then it starts decreasing. Well, if a function starts increasing and then starts decreasing, this is telling us that this point must be a maximum, right? So when f prime of x changes from negative to positive at f at 6, we know f at 6 must be a maximum. Okay, so if it goes from increasing to decreasing, guys, I got this backwards. It goes from positive to negative. F at 6 must be a maximum. Okay, if it changes from negative to positive, that means it goes decreasing, so the function is going down, hits a derivative of 0, and starts going up. That means it must be a minimum. Okay, so this is what we call the first derivative test, guys. So over here, the relative max is -6, 6. The relative min is 6, -6. Okay, a critical number of a function is a number c in the domain of f such that either f prime of c equals 0 or f prime of c does not exist. Okay, we'll talk about this more in a second. Find the critical numbers of the function. Okay, so again, what our definition said, f prime of c equals 0 or f prime of c does not exist. So in this case, let's figure out what f prime of x is. I get 4 comes down, cancels out with this 4 is x cubed minus 3x squared plus 10x. Okay, now if I factor this guy, x squared minus 3x plus, oops, I made a mistake here, guys, minus 10x. That means this is a minus 10. And this factors nicely for us as x minus 5, x plus 2. Okay. So in other words, f prime of 0 equals 0. F prime of 5 equals 0. And f prime of -2 equals 0. Okay. So therefore, 0, 5, and -2 are critical numbers. Guys, sometimes we call these guys critical values. It means the same thing. Critical numbers. Okay. All right. Find the absolute max and the absolute min of the function x cubed plus 6x squared plus 9x plus 2. Guys, I'm going to do this in Desmos because this is going to be a way better way than me trying to sketch this out. Okay, so here we go. So guys, we're kind of cheating over here because I am looking at the graph before I'm doing the algebra over here. Okay, but it's going to be now hopefully we can see, guys, that this value, it appears to be at -2, is going to be the absolute minimum. And this is the highest value is going to be f(x) equals 18. So there can be an example of our extreme value theorem. Okay, so this is a continuous function from -3.5 to 1. Okay, and we need to figure out what the absolute max is going to be 18, and the absolute min of looks like -2 is going to be. Okay, so here's how we do this guy algebraically. Step 1, we're going to figure out the derivative, and we're going to figure out our intervals of increase and decrease. So f prime of x equals 3x squared plus 12x plus 9, a common factor of 3 here. All right, so guys, there's a quick little factoring over there. Okay, now here's how my number line is going to look. It's going to start at -3.5, so it's not going to keep on going this way, and it's going to end at 1. Okay, now the values I have here still are going to have a value of -3, and then a value of -1. Okay, so let's take a number in here, say -3.25. Okay, so that'd be in between -3 and -3.5 and -3. So -3.25 would be a good test point for this guy here. The number 3 is positive. -3.25 plus 3 is negative. This is going to be a positive interval. And we can see that over here, from here to here, this function is increasing. In between -3 and -1, 3 is positive. -2 plus 3 is positive. -2 plus 1 is negative, so we're negative in this region here. And in between -1 and +1, let's say 0. Positive, 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 we're increasing over here. Okay. Now what our first derivative test means is that this point, it goes from increasing, that means the function is going up, and then starts decreasing, that this guy must be a max. Okay. And now for this one, since the function goes from decreasing to increasing, this is saying that this guy must be a local min. Okay. So let's figure out what these points are. F, so I can go out my original function to figure out what the y value at this point is. F at -3 equals, and guys, I'm just going to fire this in my calculator here. -3 cubed is -27, plus 6 times -3 squared is 9, plus 6 times 9, plus 9 times -3, plus 2. It's giving me a negative number here of sorry guys, something's messed up here. Yes, there we go. Sorry guys, made a mistake on my calculator here. There we go, and we get a value of 2. Okay, so like we see in this point over here, this point is -3, 2. Now let's figure out what this point is over here. It looks like it's -2 based on the graph, but we're going to confirm that algebraically. So f of -1, I'm going to put a -1 into my f function over here. So I get -1 plus 6 plus 9 times -1 plus 2 is -2. Okay, so this is like -1, -2. It's this point here. Okay, so now the key is over here. What the extreme value theorem says is that these points over here might be the max or the min. So this guy's only defined from this point to this point over here. So if we figure out f of -3.5, okay, and -3.5, just going to fire that in, and we get 1.125. Okay, well, this point is not a maximum or a minimum. This point over here is not bigger than this local max, and it's not smaller than this value of -2. So this guy is neither a max or a min. If we test f at 1, we go 1 cubed plus 6 times 1 squared plus 9 times 1 plus 2, and we get 18. Okay, so now this point over here, so what's this telling us? We know that this is a local max. Okay, this is a local max, but it's not the absolute max. Now -2, this is the smallest value we have between all these guys over here. So this is going to be an absolute minimum. 1.125 is neither a max nor a min. F of 1 equals 18 is the absolute max for this function over here. All right, guys, hope that makes sense over here. Okay, so this is going to be the absolute max for this function here.